So welcome back to another episode of Cinema Engineering Podcast. Today's a pretty special day. We've got our first guest on today. So when the four of us planned to do a podcast, we wrote down all the things that we would do, all the different episodes, and guest speakers were one. And today's guest was the first name I wrote down. We're real lucky. And without any further ado, I will introduce, we've got Brian Long. What we're going to be talking about today is his research papers. So some work he did with SMPTE. If you want to kind of let us know a little bit about yourself and what got you to this research paper, Brian.
Sure. I spent a number of years in loudspeaker design for one of the leading loudspeaker manufacturers and did a lot of touring work. And then I moved over to post-production. And once I got into post-production, we were working on product development. And there were a lot of notions out there on how things were actually working with regards to the X-curve and the physics of speakers and how they were working. So as we were doing this product development, we sat down and we went, well, let's actually look into this. Let's, put together a formal paper. We had gone through the research that was out there and noticed that this particular area was lacking in actual academic research and a peer-reviewed paper. So we decided to tackle the topic. And in doing so, I put together this crew and they were willing to come on this journey, which of course took a little bit longer. So the team that put this together, Roger Schwenke, Pete Soper, and Glenn Liebringen, it was a really cool team. And, this was 10 years ago and we were working across, the globe, essentially. Glenn's in Australia. And the rest of us were here on the west coast of the US.
Amazing. So we should introduce the paper, what specifically the paper covers. So further investigations and the interactions of cinema, loudspeakers and screens. So, hey, this is a really key area. I would guess pretty much every real cinema at the moment still, before micro LED takes over, is an acoustically transparent screen. And that'll be a question in a minute if transparent's a fair word to use, but an acoustically transparent screen with speakers behind it. So what effect is that screen having? What does that do to the sound? So I guess you've covered why we needed some research. There wasn't a huge amount there. I guess the general terms of the paper, did you know going in roughly what you thought screens were doing to speakers, or was the research so poor before this that you were finding out for the first time?
Well, when you're doing product development, you kind of look at what the competition is doing and you see what you can do better and where you want to focus that product. And one of the many claims that was out there is a lot of manufacturers were advertising, or at least their marketing departments were advertising screen spreading as a benefit of their loudspeaker design. Well, screen spreading, what exactly is that? And at the same time, within SMPTE and the groups of SMPTE, the cinema technical committees and whatnot, we were, having the debate about, where did the X-curve come from? The X-curve is SMPTE, Society of Motion Pictures and Television Engineers Standard ST202. And then there's a revision date after that. And ST202 mandates a frequency response for large room cinemas. And essentially what that is you're flat to about 2 kilohertz, and then it rolls off pretty drastically after 2 kilohertz. Johan Allen had written a paper on this, on how it came to be, kind of the historical context of it. And it was really an in situ thing. So I think that paper is in the bibliography here. If not, it's available. You can quickly search it out on the internet. And how that came about was very interesting. Why did that really come about? What is screen spreading? So that's what we kind of put together to really look into, because of course, the people we were working with, they believed in, flat speakers, flat phase response, high powered loudspeakers. And so, well, if you're going for this target curve, what does that mean? And what do you need to do to achieve that?
Right, absolutely. I guess that comes up later in the paper, the impact of the X-curve. So that's quite interesting, that when we look at some of the results in a minute of what the screen's done, how much of the X curve came from what we were getting after the screen was in place, and how much of the X curve is, well, that's a target, and it just happened the screen got us there.
Well, the X curve, like many things, came up because of an in situ situation. Standards, and when any industry starts, there's a small group of people, and then as the industry grows, there's a large group of people. So when you're at the small group of people at the beginning of the history of something, you're able to put together a way forward that is relatively consistent. So the history of the X curve was the translation, the perceived translation of, a flat loudspeaker to a loudspeaker in a specific room at that point in time behind a screen. And the observed measurements with the equipment from that technological era.
So we'll see in a minute that the screen happens to be playing a part in that. There is a link below. I'll put a link in the text to buy the paper we're talking about, and I'm going to bring up a few screenshots of it. I guess the first thing is to understand part of how the screen is having this effect. So if I come down to figures 7, 8, 9, so we can see that speaker that you used has an impulse response. We put the screen in play, and there are secondary, tertiary impulses. So we're getting a reflection from the screen, then back off the speaker through the screen again, or where are these impulses coming from?
So yeah, I mean, honestly, okay, this is, we're into the graphs and whatnot now, but we can start with a much easier example. So, I'm talking, I put something, like just my hand in front of my face, and my voice changes, right?
Right.
So, just like anything, well, if you put a screen in front of a speaker, what do you kind of expect it to happen? Something's going to happen. That
Sure.
air and that air pressure movement is blocked to some extent. So, great. You're putting energy into something. Where does that energy go? Some of the notions at the time, well, it spread. Well, is it actually spread? Some of the people, were saying it was, well, it's like a Fresnel lens. Well, that actually isn't kind of too far off when you look at the physics of how a Fresnel lens works. And, it's honestly exactly it. So you put an object in front of something that's emitting air pressure vibrations and energy, sound, and that energy is going to go somewhere to that object. And even if that object is porous or semi-porous, as the case may be, depending on the rigidity of that object, some of that energy is coming back. And so then the question is where does that energy go? And so in these particular graphs, you see, oh, well, some of that energy is coming back. So, when we started to look at that, and what was really cool is, the process. There's a photo in this paper of the rig, and our initial thing was, we put a sample of screen in front of, a loudspeaker, and we put it on what is essentially a high precision telescope motor. If you look at the various prediction software and, plans and setups, lots of people were at that time doing 5-degree increments of measurement, and we weren't. We were doing 1-degree increments, and you could actually do more if you wanted to, but then the data sets get unwieldy, so we felt 1 was fine. So you're able to manipulate this very precisely, very repeatedly through a measurement series, and you can see everything that's going on. So great, you get this energy that's coming back. Well, okay, what actually is going down there? And it actually is quite simple. At the end of the day, it's a little bit of basic geometry. Angle of incidence equals angle of reflection.
Right.
So that energy is going to hit at an angle, and it's going to bounce back at the appropriate angle, as well as one would expect from basic geometry.
Okay, so we've got sound hitting the screen, coming back at itself. So then that's creating comb filtering. Is that the biggest effect that we get?
That's exactly it. So okay. And there's lots of there were recommendations, of course. Well, how do you put the speaker in relation to the screen? Do you leave some space? Do you back it off? And lots of people were saying, well, you put it as close to the screen as possible. Well, okay, but what does that mean? So, in the paper, it actually gets into, there's kind of two effects of the screen, and we only really touched on above 500 hertz. And we did note what we saw below 500 hertz with one of the types of screens, and that there was a membrane-like effect that did affect lower frequencies, but it wasn't as pronounced, of course, as the higher frequencies.
Right.
So, focusing on 500 and above, that's a range of wavelengths, and certainly you have very short wavelengths in there. So if you have, a large horn type speaker, as most theatrical cinema speakers are, with directivity and whatnot, and you put that horn so that horn's touching the screen or minimally is a minimal distance from the screen. Well, what happens, that energy hits the screen, the energy that's coming back, because it's such a short distance, comes back near full energy, hits the horn at a different angle, comes back out, goes back in, comes back out, et cetera, et cetera. And so when you have that near equal energy, or, even fine 3 dB or even 6 dB down, depending on that, well, what do you get? You've essentially put multiple speakers there, and there's kind of a Fresnel effect, sort of. But that results in, high density comb filtering. So the question is, how audible is that, or what is that? What does that mean to the X curve? So when we did the data resolution on this, we showed the high resolution data with the high density comb filtering, but we also showed the smooth data. And so when you look at the smooth data, where you've taken a flat speaker, you've put it behind something that is relatively acoustically transparent, and you look at it with third octave smooth measuring, you have pretty close to the X curve before you even involve the room or whatnot. All these measurements were done in an anechoic space, so they're pretty pure.
So for a commercial presentation, ideal. When we move to residential private cinema now, we're not aiming for the X curve.
Right.
So
here's the subjective rub to that, right? You take that flat speaker, you put it behind the screen, you measure in third octave. Oh, it's the X curve. Great. Well, or it's got high frequency roll off, and you're looking at third octave. Maybe you're looking at 6 octave, whatever. You're looking at some sort of smoothing, depending on who you are. Some people look at half octave. Some people will look at whole octave smoothing. There's lots of different opinions on that. That's a different discussion. But you see some roll off. So what do? You reach for your equalizer, and you equalize it flat. Great. Your smooth result is flat. But then, go to your unsmooth result and look at this high density comb filtering. High density comb filtering is constructive interference and, additive sound. So that's great where you've got interference and it's canceled itself out. It's not great on where it's combined. And so is your smooth result really flat at that point?
Right. So that, we'll jump to a question I had later. From later in the paper, you show essentially the insertion loss that the screen's causing.
Yep.
And for one of the perforated screens, high up, so like 10K, where I think it's 8-9 dB insertion loss.
Sure. Yeah.
So if you EQ that, actually you're just creating more comb filtering, right?
Well, you've just shifted the magnitude of the comb filtering. Comb filtering, the energy relation is the same. You still put energy out at a zero level, and then it goes and comes back, and it decreases as it bounces back and forth. Now you've just offset that. So wherein, before you were putting energy at the screen equal level, right? And it ended up, kind of like this on your smooth results. Now you're putting energy at the screen like this. So you're offset. You're no longer flat behind the screen. So it's an interesting experiment, and I encourage those people who are interested to do it, honestly. And that's the thing is, honestly, so maybe you don't have a telescope motor and whatnot, but I guarantee most of the listeners, particularly those in the install companies, have access to a screen in a relatively dead room, and you can essentially replicate this experiment.
Yeah, great. It's interesting. Certainly, my own company, we have drawn some conclusions from some testing and some of the answers from a paper and a couple of other papers, and it's whether those conclusions are valid. So I pretty much now do not specify any perforated screens in private systems. The graphs to me and the results I've seen, from an audio-only perspective, so we'll ignore screen gain, we'll ignore the effects of using a woven screen. I think we get better results. But is that a conclusion that can safely be drawn? Is there ever a time from an audio only perspective that a perforated screen would be better?
The answer to that, I believe, based on the measurements, is no. But I think the question rather should be, in all cases, is a woven screen better?
Right.
And the answer to that is no. And you kind of get it in the paper. So one of the challenges in doing the paper is we had this whole set of data, massive set of data. And so we localized it down to the graphs you see in here, but we also made the entire data set available via Meyer Sound's Map Online program. So anybody who wanted to could go in and experiment and, just like we did in the paper, put the microphones in the virtual sound field and see what the result was, on axis. So to keep the paper focused, and because of the plane wave tube verification, and that was the other part of this is, okay, we've just done this experiment. Are we correct? How do we verify it? And that's where Glenn and his team came in, is they brought an entirely different method, entirely geographically separated from us, and they were able to duplicate and prove exactly what we were proving. But back to the main thing is, okay, well, everything in the paper here is with the speaker firing straight on at the screen, right? But when you're in a room, okay, here's your screen, right? And, the audience is over here and the speaker's behind here. Well, in the center, your speaker is probably straight at the screen. But when you're out here, you toe in, right? Generally speaking.
Yeah.
So when you get to looking at the speaker, the woven screen, and you look at those off-axis measurements, that off-axis on that woven screen starts to behave like a perforated screen, if not a little bit worse.
Yeah, okay.
So when you start with the speaker towed in 5-10 degrees, your woven screen ideal is compromised and beginning to already look like a perforated screen.
Yeah, okay. So,
which theoretically could account for some of the slight timbre difference left to right.
Yeah,
that we all noticed.
Sure. Okay.
But that is a pure notion. We never went so far as to do the A/B listening and whatnot. So
your graph, so I'm looking now at figures 15, 16, 17, where we look at the difference in axis. So this is almost a spinorama, section with the screen in place.
It is exactly that.
And that is the speaker moving on its axis, not the listener moving, correct?
No, actually. So it's the speaker and the screen were mounted fixed.
Okay.
And so it's both of those spinning versus the mic.
Okay. So that is essentially like an off-axis seating position. Is that right?
Correct. With a speaker dead on firing at 0 degrees inclination vertically and laterally compared to the screen.
Right.
At just the specified space.
Okay. So can we infer results of what happens if the seat and the screen stay consistent and we move the speaker? So in many projects, I'll create a baffled wall behind the screen, but it isn't straight. So my left and right are towed in and the screen is flat. So now I've got my center and my left not hitting the screen at the same angle. Can I infer results from these graphs for that situation?
No, but that's why we put the entire set in Map Online, because you could go to Map Online and you do have options not only of lateral, but vertical tilt as well.
Right.
Map Online at that time was a 2D only program, so you only get a 2D slice. If you have a screen and you're both tilted down and towed in, that data we don't have in a complex 3D.
Sure.
And we didn't at the time. It just didn't exist. It wasn't something we could do. But it could be created from the 2D slices that we have.
Yeah, sure. Okay.
So essentially the data in this paper is a gateway to what is available to the public for free outside to, really kind of dive into it and see what all those combinations were. And so, we did a baffle wall. We did, the different types of screens, and we did the different distances. But at the end of the day, it comes down to angle of incidence and angle of reflection, right?
Right.
Versus any membrane effect the screen might have. So my general rule of thumb, and it's kind of fun because I'll also do special events wherein I have massive line arrays. I'm outside. You've got these massive screens. You're doing a venue for multi thousands of people, watching a movie, right? So there you have the worst case scenario. You have a line source, so you have multiple speaker elements in a curve. So the high frequency transducers are not time aligned in the near field, right? And you've got a perforated screen. Well, then what do you do?
Right.
And so it really is that's where this data really comes in, and it's really the best proving example is if you put that line array in its full form right up next to the screen, it's not good.
Right.
But you back that line array off so that you are able to get the reflections, because often there's an empty stage house behind you. Any of that reflected sound can just go away. Right. Or you've got a lot of heavy drape. But the bottom line is you have a big cavernous space with a lot of absorption, which is generally our plan, or a lot of open air for that energy to dissipate. So you back that line array off, so any reflected energy goes out and away and doesn't hit the originating source, right, and you're suddenly in a much better situation.
Yeah, makes sense.
So, when you're looking at your speaker selection in smaller venues and cinemas or whatnot, that is my preferred conclusion of this is find the balance. Find the balance where the direct energy does not make it back to a reflecting surface, right, versus, the space you have and everything.
So I guess in a smaller room when we don't have huge areas behind the screen, am I right to think we've got two options? We can start to back away from the screen as far as we can, or we add more absorption to the baffle wall. Is absorption on the baffle wall going to help?
Oh, absolutely. Absorption on the baffle wall will help. And, the reason we chose the distances to present in the paper that we did is, there's, 6, 12, and 18 inches, yeah, right, from the face of the speaker. Let's, be careful with noting that as opposed to, maybe where the actual driver is. Right. So you would have, whatever, if you're using a horn loaded loudspeaker, you're going to have the distance in the horn and then the driver there, sure, as additional space. But, that's what the paper really illustrates is, in a case where you have only a relatively small choice of space differentiation based on how close you put that speaker is, what can you do? What might happen, Right.
So, yeah, so it's an interesting one, isn't it? I look at what we're doing as a business and I see what, some other integrators are doing. For me, the worst case in a private room is going to be an in-wall speaker and a screen mounted directly on front of it. There's nothing, right, to help, right? You've got maybe 20, 30 millimeters to the screen and it's reflecting straight back to a plasterboard drywall baffle that's not covered.
Yeah.
So
you need to have 2 inches of absorption on that. Right. I mean, that's just, and that comes from the days of THX and everything like that. And, if you look at the way, pretty much any of the actual studios do baffle walls, it's going to follow that formula. So, now, the other considerations is everything in this paper is based on a horn-loaded loudspeaker. I have seen people put, dome tweeters, behind screens, and right, that changes the game completely because you don't have that directivity control. And so that's a whole hot mess of, you got to kind of figure out what's going on there. But, and if you really want to get nuanced, one could experiment. Well, the faces of these speakers, particularly the low bass bins, they have surface area that's rigid, that's part of the cabinet structure. Yeah. If you wanted to go so far, in an experiment, you could put absorption on the, rigid non-driver surfaces of the speaker and minimize, again, reflective surfaces, yeah, once you plot that geometry.
Yeah, I mean, I've absolutely used product that comes with it. We've used in-wall speakers that have a front face of foam. It leaves the factory, mm-hmm, with foam on the baffle of the speaker. So yeah, there's definitely definitely product where the designer, I guess, has taken that into account and already factored that reflection and comb filtering because they know the application, they know where it's going to be used.
Right.
So I'm just going to look through the other questions I had planned for you because we've answered a lot of what I had. So the key thing, so we know that distance is the biggest win, right? Distance has more effect than anything else. Is that right?
It's the easiest thing to have effect. Well, the biggest thing is not just distance. Is even if you have distance, but if you have a flat reflective surface behind the screen, it doesn't matter how much distance you put. You're game over from the start. There, you need to have an absorptive environment behind the screen to capture the wavelengths that are coming back.
Right.
And baffle walls are great because they also help with low frequency control as well. And that's, in my world, a lot of the large format cinemas in a lot of the major chains, they don't do a baffle wall. They just put the speaker on some scaffolding. So there's space for the mid lows to go backwards and come forwards based off the rigid walls of that structure. And that's, outside the bounds of this paper, but that's just a whole other mess.
Right.
So, if you have a space, you fix it physically first, fix it in the design, right? You have a space, you've got your speaker placed, so it's in a proper environment of absorption and low frequency control.
Yeah.
And then number two is, your distance to the screen based on how your speaker emanates high frequencies.
Right. So that's an important
and
thing.
Your screen choice.
So part of that design is understanding the radiation pattern of the tweeter involved. So residentially, we're not always, and for private cinemas, we don't use horn-loaded speakers all the time. There's loads of different stuff we use, technologies we use, designs we use. It's not always going to be a horn. So, we're aware of the fact that there may be more insertion loss. If I'm using a soft dome tweeter that has a smaller radiation pattern, I'm probably going to get more insertion loss because I'm basically trying to throw that sound through fewer holes. If it's not radiated as much, it's got to go through a tighter section of screen. So I guess the distance helps that as well, right? Is that a key?
Well, and that's, you exactly hit it, is, when you're close to a speaker, your transducer is affecting a small amount of holes or a small amount of perforations. The further back, the more opportunities the sound has to go through the screen, whether you're woven or perforated or not.
Right.
Now, again, from the graphs, is woven, going to be more transparent? Generally speaking, yes. The more straight fired on that speaker is, yes. But then you got to look at that versus the coverage pattern.
Right.
Particularly on your left and right is, okay, well, what's happening there? And it's all trade-offs, trade-offs. So you got to come to the best case with all the factors. You can't just, people can't just huck a speaker behind the screen and go, yeah, this is the way it's going to be.
Right. And hey, that's the game, isn't it? Balancing compromise. That's the whole game. That's probably the biggest learning, I think, from the work we do in the R10 committee, the CDA CTA R10, that obviously Peter chairs, that understanding that it's iterative, we're going to go around in circles, and we're just going to keep trying to minimize compromise. We can never remove them. If we're putting speakers behind the screen, there will be compromises, right? So it's just how much
you have to identify your mitigating factors and come up with the best balance between all of them. The other thing is too, with dome tweeters and even ribbon drivers and stuff like that, the patterns, frequency dependent, the patterns may not be designed for wide area coverage,
right?
And so that can cause a whole different set of considerations and whatnot. So it really comes down to knowing the product you're using and how to get the best recipe with all the ingredients combined.
Amazing. I mean, that's perfect. The key thing for me is to really kind of highlight this research and make sure that people in the industry are aware how much impact the screen's going to have and aware of the decisions they can make to mitigate it. So we're going to look at the type of transducer, the distance we place it, the absorption, the screen material, the angle it's firing at. So there's a lot, right? There's a lot of different things that we need to take into account. So that's great, isn't it? This one, See, this is a bit that to me, figure 21, that's a bit that I'm guilty of looking at figure 21 and saying, I need to just stop selling perforated screens. Woven screens just behave nicer.
On the whole, they do.
Right.
You know, but if you've got a situation where, you know, you've got, say, a large woven screen and your toe end of your speaker is, you know, 15, 20 degrees with relation to that screen installed with a declination of, you know, 5 to 10 degrees, you know, then your mic position when you're on the close side of the audience, you're already 40 degrees off axis,
right?
You know, and so that's when you look at those other graphs from the speaker firing straight on and you go, what is, you know, speaker straight on woven screen, mic 40 degrees off axis look like? And you go, oh, that's not quite as good as I thought it was, you know?
No, that's key, isn't it?
But that's not what people are going to advertise, you know?
No, hey, it's interesting looking at data sheets when we see manufacturers saying what the insertion loss of their screen is, and whether they have. Sometimes you see a small bullet point, you know, in the footnotes that it was measured at 0.5 meter.
Yeah,
well,
exactly.
Great, you know, that's ideal. You know, if we can get 0.5 meter in a private room, you know, if I try that in London with high land prices, you know, 0.5 meter,
you might get that.
Yeah, right. But you know, 0.5 meter.
Your seating position might be a 0.5 meter because you know that's all the bigger the room.
So 0.5 meter behind the screen in London is expensive. So the reality is, I'm not always going to get it. More times than not, I won't get 0.5 meter behind the screen in London. So we've got to look at other ways to mitigate it. If I've got to go close, then maybe I can use a different speaker or a different screen material or more absorption. So how the other ways to mitigate it? That's interesting, isn't it? You know, you show in your table 1, as we get down to page 58 of this paper, some of the insertion loss. Is that where we're at? Is this on the absorption?
Yeah. So this is broadband absorption.
Right.
Loss.
Okay.
Is it loss? No,
right.
Not really. It just means the energy has gone somewhere that the screen hasn't incurred the loss per se. It's redirected the energy and it's dissipated elsewhere.
Right, exactly.
But, you know, when you're on the audience side of the screen, sure, you see, oh, well, those frequencies have gone away in a smooth portion. That's loss.
Right.
So it technically is loss, but it's not loss.
No, absolutely. Okay. So it's not, we're not professing that the fabric is absorbing all of that energy. It's not being lost into the fabric. It's being lost as a result of the interaction.
Right. And the environment and whatnot. Yeah, because that was one of those things, you know, one of those terms that we treaded very carefully on, is it was called screen loss.
Right.
You know, well, how? You know, I mean, and it just doesn't. The mechanism, you know, the mechanics and the physics of the screen don't absorb energy.
No. Okay. And then I guess we put other fabric into most of our rooms that has slightly different considerations, I guess. And when we surround speakers will be behind fabric that isn't as translucent as the screen, almost certainly. It probably isn't.
Well, it depends on the fabric, but yeah.
Yeah, absolutely. And you know, so in many cases, I would think the screen is more translucent than the fabric we use in the rest of the room, and therefore we're attempting to put surround speakers further away from that to help as much as we can. But I guess that fabric is having an interaction from the other side. It's not, you know, we're not just hitting it from speaker side. So is there any absorption? Like, do you think these screen fabrics are really absorbing anything hitting them from the other side, or is it just irrelevant?
No, I mean, you know, okay, so, you know, they're symmetrical, essentially. Like, if you turn the screen around or a grill fabric around, does it make a difference? No.
Right.
You know, it's still going to have the same effect. So coming and going, it has the same effect.
Okay.
You know?
So, yeah, right. Okay. So the reflectivity that you measure, that you show, that has the same effect. So any sound that's already in the room that hits the screen, we're going to see the
it's going to do the same thing.
Amount that's reflected back. So that absorptive material we've got behind it So that really high frequency will never get back to it, will it?
Yeah, pretty much. I mean, and you prove that by, okay, fine. You put a speaker on one side of the screen, speaker on the other, and you turn one on, measure one side, you turn one on, measure the other side. You're going to see if you're using the same speaker type, the same behavior. And so like, what's cool, and there's some graphs in there that show exactly what we're talking about, and it shows the acoustic shadow
Right.
created by the speaker, and then these flares coming off the side of the speaker of directed energy,
Yeah. Right. Here,
So, but I mean, basically when you're on the opposite side, you have people talking and whatnot. And yeah, that, you're going to have stuff come back, but it's not. And, if you have surrounds, sure, you're going to shoot energy at the screen and you're going to get some bounce back. Absolutely. And, we hear it in large rooms and things like that, because in many times the screen is the most reflective surface.
Right.
So yeah, I mean, but okay, when you're looking at surrounds in rooms or speakers on the other side of the room, where is their principal aiming? You don't want to fire them directly at the screen. You want to make sure that the screen is far off axis. So depending on the room and the geometry of the seating plan, I would expect that high frequency transducer to be, essentially down 20, 30 degrees.
Right.
So yeah, I mean, if it's 100-degree, or just a conical thing, horfing stuff out that's not directly controlled, yeah, you're going to get stuff going at the screen. And, if you took that speaker in, and measured it solo, if you're able to window it out from the rest of the system, put noise through a single speaker and measure it, yeah, you would see essentially something like the graphs that we see for the behind the screen. You're going to see an impulse coming back from the screen based on how far that screen is.
Right.
From the speaker and the measurement point, obviously.
Okay. And the impulse itself, the impulses we see at the very start, I guess the impulse itself isn't particularly audible, right? We're looking at, maybe 80 dB down. It's the comb filtering that's audible, not the impulse. Is that right?
Right. And, there's great debates out there. How audible is this comb filtering? How audible are these reflections? And so that's why I use the example, put your hand in front of your mouth. And, does somebody listening to you notice a change in timbre?
Right.
And even if you put your hand in front of your mouth and spread it out a little bit, right? So look, I've just perforated the screen from my mouth. So, do the experiment is all don't trust the notions. This is a pretty, at the end of the day, it's a pretty basic thing that you can replicate, even if you're just listening.
Sure. And at arm's length, I guess arm's length hand makes very little difference, right? So, right. we're showing that the effect that distance has.
Exactly. And the thing is, when you're doing these measurements, it has to be a time inclusive measurement. It has to be a transfer function with an FFT. You can't do this with an RTA. And a lot of the meters now are FFT based RTAs, so they do bucketing and stuff like that. But unless you're doing something, with many of the varying products out there, you need to be able to see the time domain and the phase domain to really make sense of what's going on.
Yeah, absolutely. It's this is one of the keys that we'll talk about more in the future on the podcast, of how to take some of those measurements and the different measurements we use.
Yeah, and in addition to that, not only RTAs, but the auto EQ algorithms are getting better. And I've been one of those staunch people that has been very anti auto EQ in my career. And we're seeing some products which I think aren't half bad, and, certainly have usable. But, if your formula is, I'm going to install and I'm going to do a good install and wire it up, and then I'm just going to press the auto button, what are you losing in, your understanding of what that system actually does?
Right.
So, if you get all this theory and whatnot, you can definitely hit the auto EQ button and, be reasonably sure. So, that is, you get into that calibration conversation, that's the thing is, the automatic button is not necessarily the greatest thing, but it could be a very good thing.
Right. I guess there's maybe a trade-off in the kind of install where the auto button's just hit and that's it, is maybe the same install where care wasn't paid to minimizing the compromise in the first place. So we've probably got double trouble that if that's all the calibration is just auto, walk away, hand over, done. It probably there probably wasn't the care and attention to make sure that the absorption's right, the distance is right, the right speakers and screen were chosen. We're probably in a bit of problems. There's probably some issues gonna arrive there.
And then there's a whole question of what should your target curve be for home, for a small room or whatnot, when you've got a screen involved and depending on what you've chosen, you have or don't have this high density comb filter. Is flat the way to be? Is it not the way to be? Certainly, the X curve is definitely not the way to be, because that's just not the situation you're in right there. But, is it something there in between, rule or flat? So that's a whole other can of worms.
Yeah, I mean, hey, that is interesting. I see different calibrators do slightly different things, and the reality is often the natural roll off is probably enough. In many systems, it doesn't need a big EQing down of high frequency, because we probably have got some of that from different axial response from the screen, from other things happening, speakers themselves having roll off. So yeah, that's interesting that different calibrators, I guess, have a slightly different take on that, because we've not got an X curve for home, right? There's no right or wrong of what that roll off should look like.
Right.
So yeah,
and it's a whole different content presentation as well.
Yes.
Some people are more music based, some people are more movie based. Even if it is a cinema room, they might do a lot of music listening. So
yeah, probably best not to just roll off aggressively in the next curve and then think you can listen to music on it.
No, that would be a very bad idea. But also, not the greatest idea to maybe EQ it rule or flat, based on what your screen choice was and your, absorptive situation behind the screen is.
Right. Absolutely. Well, thank you very much, Brian. I think we've got some real key information there. That's ideal. So we now know when we're doing each design, the kind of 4 or 5 things we need to look at, what's going on behind that screen, the screen itself, and everything behind it.
For sure.
Amazing. Thank you very much, buddy. I really appreciate it. And
Ben, thank you very much.
We'll catch up on an R10 call soon.
Sounds good.
Cheers,
Talk
buddy.
to you soon.